Hello, welcome back. In this segment, I will discuss an interesting river crossing puzzle. You have a farmer and three items, namely wolf, goat, and cabbage. The task of the farmer is to transfer all of those three items to the other end of the river. Of course, there are constraints. The boat is too small, so only one item can be carried in addition to the farmer. And the boat cannot be left alone, meaning you cannot put a goat alone and ask the goat to transfer from one side to another side. The farmer must accompany the items on the boat. Okay. And you cannot leave the wolf and goat unsupervised without farmer. Similarly, you cannot leave goat with cabbage unsupervised without the farmer. Okay. The goal of this puzzle is to securely transfer all of those four items, of course, including the farmer, to the other side. I'll transfer this problem into a Boolean satisfiability problem and then use a logic solver like Z3 to solve this puzzle. Okay, so in order to go there, right, we need to encode this problem as a logic problem. So how do we go about doing that first? The idea is fairly straightforward. We will identify Boolean variables. There must be a Boolean variable for each of the items we have. Okay, so how do we represent the state of the system at any moment? So the state of the system at any moment is made of farmer, right? Where the farmer is at ith step, wolf at the ith step, goat, ith step, and cabbage. Okay, so at the beginning, we can assume all of them are on the left-hand side. At the end, we need to transfer all of them to the right-hand side. So what is beginning, what is end need to be defined more precisely. And for that, we can assume former of 0 equal to true. Similarly, all the other items. So to end the puzzle, we need to say the goal is to come to the other side, which means after, say, we don't know exactly how many steps. Let's assume some number of steps. Yeah, n steps. We will have all of them here. The array index is basically step number. Okay, so we want all of them to be on the other side. But the question is, how do we get from this initial state to this final state? So this is the goal. So we need to build a state transition system that will define rules of the game. Okay. What you're seeing here is my Python Z3 version of the river crossing puzzle. As explained on the whiteboard, we need to identify state variables like farmer, wolf, goat, and cabbage. We don't know the number of steps to solve the problem. Therefore, I take that as a parameter. We will have an array of states for farmer, wolf, goat, and cabbage. That's the reason why you see a for loop here. So initially, we want the farmer, wolf, goat, cabbage to be on the initial bank, all of them to be true. That's the reason why we have this. At the end, the final state is all of them to be false. That's the reason why you see a not in the front. Constraints now. What are the constraints? The constraints are as follows. What is the first constraint? The farmer must move each item. That means the board cannot be left alone to move from one end to another end. How do we encode that? You see here, the state of the farmer at the ith step cannot be the same as the state of the farmer at I plus 1 step. That means the formers keep on changing from true to false, false to true, all those things, right? Similarly, we said only one item can move with the former at a time. And if an item moves, it must move with the former. How do we model that part? Let's say item moved from I state to I plus 1 state. Item of I is not the same as item of I plus 1, right? That is the meaning of move, which means the former value at ith position is same as the item's position. Okay, that is the reason why we have here an implied statement. When item has moved from ith state to I plus 1 state, right? Item of I not equal to item of I plus 1, the former better be together with item. That is the reason why we have an equal here. Okay. How do we model at most one item can move with former? That is also an interesting question. We can create two for loops over the list of items we have, excluding the former. And we say that, let's assume two things moved. Okay. In that case, what will happen? Both of these will be false, right? This will be false. This will be false. And because of an OR statement, the whole thing will be false, which is not what we want. That's the reason why we say only one thing can move at most with the former. If two things move, this will be false. From a satisfiability point of view, no solution will be found. So we want to make sure that only one item can move with the former. That is the reason why we index j and k for all of the items and making sure that, as you can see, the kth index starts from j plus 1. So we take one particular item, and let's say wolf. We make sure wolf and goat simultaneously do not change the state. Similarly, wolf and cabbage do not change the state simultaneously. Similarly, goat and cabbage. Okay, that's basically what we are doing here. All right, then another important thing, of course, is that we cannot leave wolf and goat alone, right? Otherwise, the wolf will eat the goat. How do we encode that property? Let's assume farmer is on the other end of the bank compared to the wolf and the goat. What we want to make sure is that wolf is not at the same state as goat for any I, right? That is the reason why we have this part. Yeah, it takes a little bit of time to get used to this kind of encoding, but essentially, once you have managed to write it in a precise language like this, you can automatically find a solution. Similarly, goat and cabbage cannot be left alone, right? Let's say farmer is away from both goat and from cabbage, then we want to make sure both goat and cabbage are at the different end of the banks. Okay, that is the reason why we have it. Right, if the solution exists, we now ask the solver to find a solution. If it exists, we do a pretty printing here to show you, what are the items on the one end of the bank and then what are the items on the other end of the bank. One end is very simple, right? The left hand is the starting end is basically if the variable Boolean value for that particular variable is true, that means we are on the starting side. If it is false, we are on the other end of the river bank. Okay. And since we don't know the number of steps, we try it in a brute force fashion. From 3 steps to 20, we can configure it, right? This is our parameterized. Okay, we try for each until we find a success. If it is success, Boolean set will be true and we stop there. Okay, let's go ahead and run it and see how it behaves. River crossing puzzle. Okay, found a solution in 8 steps and we can read it very quickly. One side is the starting bank, other side is the ending bank. On the starting side, we have farmer, wolf, goat, cabbage. At the end, we reached farmer, wolf, goat, cabbage. That's good. So we can see the state transition. The farmer decided to take goat. That's the reason why you see here he left wolf and cabbage here and got farmer and goat here. And then the farmer decided to leave the goat here and come here other side. So we have farmer, wolf, cabbage. So and then he taking cabbage and he can't leave goat and cabbage. So he's taking the goat back. So here and then he's taking the goat. He'll drop the wolf other side. Wolf doesn't like cabbage, so they both are safe. Then the farmer comes back and take the goat. All of these satisfy the constraints we have outlined. You have a starting bank and the ending bank, and the state transition is automatically generated based on the logic description we have had. Okay. So that's basically it. The idea is convert the requirements into proposition logic statements and let the solver explore the state space based on the rules of the transitions that we have defined. Yeah, thank you very much for your attention.